Hello, everyone. How's everybody doing? I hope you're doing fine. And today we have a very, very exciting day. We are going to be talking about planes, specifically the circle. When we're done with that, we're going to continue with nothing. Now, how exciting is all that? So, if you have something better to do, don't do it. Stick around and we'll have a lot of fun just finding out what these things are, nothing and circles and planes and etc. What they are. We'll find out. Before I get into that, just want to remind everyone that we've got one more time. I always do this. In about 3 months, June 8th, we have our 7th Rational Physics Conference in Bora, Sweden. So I'll keep reminding you so that you make your reservations if you plan to go. Okay. And hopefully we'll see you there. You'll find some very, very interesting people, that go to these conferences, and they're very smart, and they have their opinions, strong opinions. Good time to exchange your ideas. Anyways, the other day I was talking a little bit. I haven't talked much about the world of flatland, of planes. I talked about points, talked about lines, didn't really get into planes. Not really a very exciting subject, but there's a couple points that I'd like to mention. And I kind of hinted at them the other day when I said, that there was this fellow Timothy Ferris, and he wrote in his book. He really has a drawing in there, which was not true flatland. And I want to go over that a little bit today. Why is flatland important? Um, when when the relativists want you to conceptualize, visualize the four-dimensional world out there, the unimaginable four-dimensional world, what they do is they say, look, you can't imagine it. You can only do it by analogy. And the way it works is that, you got to imagine a flatlander trying to imagine our three-dimensional world. And if you can visualize that, the problems he would have, or the conceptual problems he would have, the square and the circle, trying to understand the world of spheres and cubes, then more or less you'll get an idea why you cannot imagine the fourth dimension. But at the same time, it gives you an idea that first, you can imagine why there's a problem first, and second, just like the flatlander might conclude erroneously, obviously, that there is no three-dimensional world because he's never seen it. But the only way you can make him see it is like Dr. Quantum did by sticking his finger into flatland, and the flatlanders trying to figure out where that finger came from, just going through their world. And just like they don't imagine that a three-dimensional world can exist, you could in the same way make the same error and conclude that that there isn't a four-dimensional world. And this is essentially their argument, that you got to do it by analogy, and the fact that you have to do it only by analogy doesn't mean it's not there. And what that really does is take them into this other argument where they talk about multi-dimensionals. Once you get past the fourth dimension, the rest is easy. You can go into the 10th dimension like string theory has, or 11th or 26th dimension. They have all these theories out there. And so once you get past that fourth dimension, it's a piece of cake. Then you don't have to imagine any of them. In fact, you can't. And so, okay, so last time I showed you that there was a problem with Dr. Quantum's flatland. It goes something like this. Dr. Quantum visits the flatland world, and there's several problems with the conceptualization when they made this little cartoon there. And that's first that things move. First, he's got to go through a tunnel really to get there, but let's forget about that for a second. He sticks his finger in there, but you can see they're all cubes. they're not squares. He's looking at them from the top. Now here's a top view, okay, of the crossroads, and you can see that he can see her, Miss Flatland, and he can see the coin she's got in her safe. And they're all 3D because they can move around. You can see the door is even 3D because it's above a surface. That's why it can move. In fact, just the fact that figures can move shows you that they're not flat. It's already conceptually a three-dimensional world that they're uh, portraying here. Okay, and you might say, well, yeah, okay, they had to do a little movie somehow, and so they had to move the Flatlanders around to make it more or less interesting and so on. Yeah, okay. I'm just saying we have a problem first with the motion of circles and other figures. And, that's not totally trivial because remember that the purpose of the analogy is to say, look, there are 4D beings out there, or there's a four-dimensional world out there, and we puny 3D beings, we have no way of knowing how these people move out there, these four-dimensional beings. See, we can move around because we're very flexible. Why? Because we are made of many parts. But triangles, squares, and circles, to give them life is a bit of a problem because once you give them life, they get all distorted. They're no longer triangles, they're no longer squares, and they're no longer circles. That's the problem. You can't move a figure without it distorting. Now you might say, well, the figure moves as a whole, right? There's no distortion because the circle moves as a circle. It doesn't distort in any way. But see, we distort. We three-dimensional beings, we distort. And we say, well, yeah, we can't picture the four-dimensional world because, we can only do it by analogy from Flatland to us. But it turns out that Flatlanders, they can't move because if they have the flexibility like we do, then they would lose their circular. They wouldn't be circles, they wouldn't be triangles, they wouldn't be squares. And that means it's not a very fair analogy to say, or straightforward analogy to say, look, a square is to us like we are to the four-dimensional beings. That's what I'm getting at. That's not true. Okay, but let's look at where all this started. Flatland was introduced by Mr. Abbott. He was a mathematician. He was also a theologian, but he was also a mathematician. And what he did, he wrote a book called Flatland in which he allegedly portrayed the two-dimensional world of Flatland. And he took it more or less like Gulliver's Travel as as a satire of British society. So, they had the certain figures represent the high class, others represent women, and so on down the line. So he made fun of them. Okay, so that was part of the reason for this work, this book. But what survived out of that are the dimensions, because that's what relativity uses. Okay, so keep that in mind. So how does Mr. Square, the one who writes this book, this is the author, A Square, how does he present his world? And he says, imagine a vast sheet of paper on which straight lines, triangles, squares, pentagons, hexagons, and other figures, instead of remaining fixed in their places, we already have that problem there, move freely about or on or in the surface, but without the power of rising above or sinking below it. Well, if they're on the surface, for sure, they're rising, they're already above the surface, okay? But let's concede that, very much like shadows, only hard and with luminous edges. And you will then have a pretty correct notion of my country and countrymen, okay? Take, for example, look at this now, an equilateral triangle. Who represents with us a tradesman? Okay, so he assigns triangles to tradesmen. Okay, fine. If your eyes were quite on the level of the table, and that is how we see him in Flatland, you would see nothing but a straight line. Not true. Absolutely not true. And you can see in his picture, he's got this triangle and he flattens it out or just bends it over or whatever he's doing to it. And he ends up with a line. He says, see, you end up with a line. No, you don't. Okay, you don't. You end up with nothing. You shouldn't see anything sideways if it's a flat surface. Flat, means that sideways you can't see it. Nevertheless, I want you to notice that the triangle is changing its shape. Okay, now you might say, well, what does that matter? Well, I'll show you in a minute, but just keep that in mind. And he says in section 6 of recognition by sight, this is how the flatlanders see each other. All figures in flatland present the appearance of a straight line. Well, if that's a straight line that you see there, then it should be two-dimensional, but not in a flat direction, not in your line of sight, but upwards. So, you know, if this line is the edge of a triangle, we are looking at a three-dimensional world. Okay? If I see this edgewise and I see 2 dimensions, there's a third dimension which stretches right behind it. So we don't see a line. If we see a line, we're in solid land. We're not in flat land. And that's the main misconception that you'll see in all pictorial representations of flatland made by, mathematicians, because obviously they had no clue, as far as how to illustrate flatland in such a way that it stays within flatland. And just let me get back to this tilting issue. He says, they see each other like a line. Well, again, that's not true. And here you'll see that we have a square. Wait till it starts here. We start with a square, okay, here in a minute. And if you tilt the square backwards, you turn it into a rectangle. It's no longer a square. That's what I see in front of me. That's objectively what's in front of me. If you keep tilting it, you don't end up with a line. You end up with nothing. You can't see a square, sideways. You can't see it along the edge. You shouldn't. If you do, then you're looking at 3 dimensions. And here's the same thing for the circle. Here's a circle. You flatten it out. You end up with an ellipse. And if you keep flattening it out, you don't end up with a line. If you keep going, you should end up with absolutely nothing. You shouldn't see a circle sideways, along the line of sight if it's lying down. There's no such thing. And as you lie it down, it turns from a circle into an ellipse. Okay? So it's not true. Their idea that they can move things around like backwards or sideways, it's not true. Circles and squares and triangles are always, always, always the side of a geometric figure. Cube could be, square can be the side of a cube. A circle can be the edge of a cylinder, a triangle maybe of a pyramid. It's always a 3-dimension. It's a face of a 3-dimensional entity. That's the only way you can conceptualize. In other words, whenever you see a circle, you got to think in 3D. You got to say there's something behind it, because there's no such thing as a standalone circle or a standalone square. This is imaginary. Even if we go completely imaginary, all we can say about squares is that they're the side of, say, a cube, or it could be an elongated, rectangular type of cube, a 3D solid of some kind. But it's always the face of a solid. Okay? So there's no such thing as 2D all by itself. It's always 3D. That's the only thing we can imagine. And then when you're looking at 2D, you're looking at a face of some 3D entity. Okay? Okay, how's the circle in relativity? Well, it's a little fancier. We start with Euclid's circle, and you can see that he started out with a misdefinition, because he says in definition 14 that a figure is that which is contained by any boundary or boundaries. He's saying that it's a figure, it's a plane. Remember, we're talking about a plane in the case of a circle. And that's not what he's showing us. What he's showing us, he says, you have all these rays, these spokes of the wheel, and you get infinite number of them, fine. You just keep putting spokes in there. You will never build a continuous surface. You can't. Not if you're going to define the circle in terms of rays or spokes or whatever you want to call those lines there. So what he's saying is that, the circle is a plane figure contained by one line, which is a circular line. Remember, Euclid's line could be a curve or a straight line, either one. He specifies straight line when he wants to talk about a straight line. In this case, he's using the notion of a curved line. Okay, so he says it's contained by one line such that all straight lines falling upon it from one point among those lines within the figure equal one another. So again, what Euclid has done is just build a wheel. He hasn't built a plane. He cannot account for the spaces between the spokes, in other words. Okay, fortunately, that was 2,000 years ago. We must have done better since then. Well, all we did was mess up even worse. We got rid of the spokes, of the rays, and what we left are the points. And so the question is, are we talking about a geometric figure or are we talking about a ring? Because it says a set of points whose distance to a fixed point, the center, is a fixed positive number, the radius is a circle. So what the new notion of a circle is that it's a ring that has equidistant points from a point in the center. Nothing in between the points on the outside to the point on the inside. And really that's the snake oil that sold you. That's what they advertise, but that's not what you got in the mail. What you got in the mail is something different. What they're talking about is that all these points, you got to build them one by one. And since between any 2 points on the circumference, there's an infinite number of points, the mathematicians are still building their circles since the days of Euclid. What they're talking about is a movie, not a standalone figure. They're not pointing to a figure. They say, look, this is how you build it. You got to build it point by point, and we're still building it because, in mathematics, we know that every point between any 2 points, there can be still yet, another point. So the famous circle of mathematical physics of today, of geometry of today, is a movie. It's not a standalone figure that you point to like, oh, there's a circle. Okay, there's no such thing. The circle of today is build it point by point, and they're still building it because there's infinite points between any 2 points on the circumference. Period. We're done. So they sold you a movie when you asked for a photograph. Okay, just in case you say, well, Bill, is that really true? And here you have the disk of mathematics. See, the circle is a ring, but the disk is the true circle that when we talk about a plane figure, a geometric figure, then we're talking about a continuous surface. Really not a surface because it's known as a plane. It's flat, completely flat. And if you go to Wikipedia, you'll find that it's bounded. This plane is bounded by a circle. That's what a disk is. It's the region in a plane bounded by a circle. So the circle, again, is taken to be just the circumference. It's a synonym of circumference. That's what the circle has become. And why is that a problem? Well, it's a problem, first of all, because of the following. If a square is a side of a cube, example, right? You have a square as a side of a cube. Is a square just a perimeter? Is just the frame? No. When we talk about a square, we talk about the plane figure, the flat, I was going to say rectangular, squarish figure that you see in front of you, the whole thing. But now for the circle, they say, oh no, the circle is everything except, it's a donut. It's everything except what's in the middle. It's just the circumference. It's just the hula hoop or the ring or the halo or whatever you want to call it. So we have a difference between all other geometric figures, plane geometric figures, and the circle. The circle is in a class by itself because it's not a plane. It's just a circle. It's like it's a line. That's what it is. I mean, if we're going to use their definitions, we're going to say that the circle is one-dimensional because that's essentially what they're talking about. They're saying, we're only looking at the ring, but that's not the case for all others. A triangle is considered to be, a plane, the whole thing from line to line, and so is a square. Okay. Okay. Does the nonsense stop there? No, it gets even worse, because what they have done in the 19th century, especially two mathematicians, one was Riemann, the other one was Lobachevsky, Russian guy, and what these two did is they started putting some of these planes, especially the triangle, they started putting it on solids. But instead of putting it on the face of a squarish type solid, like, a cube or a rectangular cube, some box of sorts. No, they started, or even a pyramid for that matter. No, they started putting it on curved surfaces, okay? And they ended up with this triangle, okay? This triangle, you put it on a sphere, now it's curved. It's a curved triangle, okay? And that's Riemann's triangle. Here's Lobachevsky. He puts it on a saddle, and it's curved in the opposite direction. Instead of inwards, it's outwards. Instead of concave, it's convex. And they talk about angles. I mean, if you're going to talk about triangles, you're talking about three angles. So what kind of angles can you measure on a curve? I mean, if the triangle sits on a sphere, it's got curved lines. You can call them curved angles. So how do they measure that? Well, they cheat. That's what they did. They figured out a way of doing it. And the way they do it is they put these tangents, and they measure the angle between the straight lines, not between the curved lines. Okay, you see how they do this? So you wonder why later on they're going to end up in general relativity with curved dimensions. I mean, you heard of length, width, and height? Well, think again. Now we have, curved length, curved width, and curved height. So these are no longer three-dimensional in the sense that, they point 90 degrees to each other. No, now they're curved. So you got curved dimensions. They had to bend the dimensions to fit their mathematics in there. Oh, my God. Anyways, you'd say, well, okay, Bill, that was 100 years ago, Abbott and all these fellows. Well, like I said last time, we come to Mr. Timothy Ferris, and he's not a nobody, okay? He's quite a writer. He's considered a popularizer of relativity, one of the primary ones, in fact, maybe right up there with Carl Sagan. And his book, Coming of Age in the Milky Way, it's been translated into 15 languages. New York Times gave it, a good reading, a good review. Says Ferris made 3 documentary films: The Creation of the Universe, Life Beyond Earth, and Seeing in the Dark. Okay, so he's involved with physics. Okay. He produced the Voyager phonograph record that was sent out of the solar system. That was a project that he did with Carl Sagan. And he's considered the best popular science writer in the English language, by at least the Christian Science Monitor, the best science writer of his generation by the Washington Post, and so on. So he's got a lot of titles, okay? He's got a lot of prizes and so on. He's recognized in the industry as a popularizer, an important popularizer. So what does this popularizer say? Well, here it is. If you look at Coming of Age in the Milky Way, which unfortunately I had to read, or I did read, I wasted my time, but here it is. This is how he presents the world of flatland, okay? And he says, 2-dimensional inhabitants of a finite universe must confront the paradox of an edge to their cosmos. And you can see the so-called flatlander who's standing perpendicular to width and length. Here you have this guy standing height-wise. Okay, fine. He's standing at the edge of the universe, the edge of his cosmos, right? But if we add a dimension curving the place on which they live into a sphere, which is that B there at the bottom left, okay, he's going to curve it around. He's going to curve their rug, their carpet. He's going to curve it around, turn it into a ball, okay? And he says, their world, though still finite, becomes unbounded. How did they figure that one out? So general relativity reveals a similar prospect for the four-dimensional geometry of the universe. Okay, fine. What have they done? They use this notion of finite but unbounded. And what are they referring to? The finite refers to the sphere. All objects are finite. Even I'm finite. You know, I stop at my skin. So every object in the world is finite because finite, in a sense, is a synonym of what an object is. On the other hand, when he talks about the unbounded part, and he's suggesting that the universe is unbounded, and that's what general relativists say, that the universe is finite but unbounded. The unbounded part means that you're going to walk all around space-time forever. That's the unbounded part. And in that sense, every object in the universe, without being four-dimensional, right, is unbounded. I mean, I can walk all over you and forever, you know, around your perimeter in your body or whatever. So every object in the universe is unbounded in that sense because they're comparing apples and oranges. See, but they're using the unbounded part to refer to the same universe. They say it's a closed unbounded universe or a finite unbounded universe. What do they mean by that? They try to get another of those famous dualities. They said, look, it's finite, but you can walk around it forever. No kidding. So does that tell us anything? I mean, what have they learned with all this? And you can see, you know, that all of this is misconceived. We don't know what a circle is because they misconceived the circle. You know, I can tell you what a circle is. I point and say circle. What I'm pointing to, that's a circle. You know, so round whatever. But to say that, look, this is a circle. It's the equidistant points from a center point. That's not a circle. That's a ring. And they're still building that ring because, you know, there's always a point between any 2 points. We're talking about locations, obviously, right? Because if they could tell me the size of the point, you know, I could say, okay, if it's 1 centimeter, there's only so many points you can put around a circle or, you know, a circumference. That's not what they're saying. They're saying the famous point is really a location. There's infinite locations between any 2 points. In other words, you can count incessantly the number of locations between any 2 locations. That's what they're saying. And so their circle is still in construction. They'll never finish it. Okay? So the circle is misconceived. The triangle used to be a triangle until these guys came along in the 19th century and started putting it on saddles and on spheres. And now they said, well, you know, it's no longer a triangle because, you know, what kind of angles can you have on a curved surface? Well, they fixed that too. They said, well, put a tangent on the circle, or, you know, wherever it touches, that's going to be the tangent. And we just take those straight lines and we have an angle. So that's how they made their curved triangles, you know, triangles. They did it with tangents. And you can see that every time they twist it and move these things, it loses its shape. But they see, you get a square, and as soon as you move it in any direction, from your point of view, it's already turned into a rectangle, for sure. And they keep calling it a square. And it's not a square. No longer are you staring at a square because a square is supposedly only seen, you know, face head on, you know, face to face. As soon as you tilt it a little bit, it's no longer a square. Now you turn your famous square into a rectangle. And they don't care about these things, you know, their conceptualization is completely off. Okay, that's enough for Flatland. Let's now work on where I left off last time, which is on nothing. Maybe a more exciting subject. We go from planes to nothing. Let's go with nothing. Last time I left you with Mr. Lawrence Krauss, and he wrote a book, A Universe from Nothing. Okay, And what Krauss argues, and he's also been on a couple programs saying this just in case, he says that matter, in this case he uses the word universe in lieu of matter, he says the universe came from nothing. That's his argument. And so what was the problem with that? Well, I had several problems. The first is the word universe. Okay. What's wrong with the word universe? Well, he's got a funny definition for the word universe, and he says that on Joe Rogan's program. He says first he confuses the word universe, because he's saying that a universe is essentially a galaxy, but one that's beyond our see or touch senses. In other words, one with which we can't interact anymore at this point and from here on forever. So he considers that a universe. He considers any matter with which we cannot interact anymore as part of another universe. And so you ask him, well, I mean, did we all start from the same Big Bang? He'll say yes. It all started from the same Big Bang, but they're so far away from a practical point of view, from a pragmatic point of view, or, if you want to do what is called type of definition. The word escaped me right now. Like a pragmatic definition or what do you call it? Operational definition. That's what I wanted to say. If you want to have an operational definition, then it's practical to say, well, anything that we can't see or touch, we'll call that a universe, a separate universe. In other words, what he's doing essentially is saying that the universe, our universe, stops where our line of sight stops. Essentially, that's what he's saying. Okay. Okay. Had a glitch here. Okay. Anyways, he's saying also, it's this universe, this matter, it uses the same space we do. And if you define universe as space and matter, all the space and matter, even that matter that you can't see or interact with, then there's only one universe. Period. I mean, that's what it used to be. So he hasn't done anything except redefine and call galaxies which we can't see. He calls them universes. And that's very confusing because he doesn't have to justify what separates us from that universe. That's where the problem is. See, if there's only one space out there, and the space is the same for all matter out there, then there's only one universe. But if you say, well, that's not my definition. My definition is anything I can't see or touch, that's a different universe. Then he's referring just to the matter. And he doesn't have to justify the whatever medium, in this case space, separates us. That's what he's avoiding by saying a universe is just another galaxy that we can't see or touch. Okay, that's with the universe part. Now, what's wrong with nothing? The nothing part. He said the universe comes from nothing. Well, the nothing part also suffers from some problems, big problems, in fact. And it turns out that Krauss, like all of mathematical physics, essentially saying that nothing is always something. They always end up with something. You never end up with nothing being nothing. It always ends up being something. And Krauss, in his exposition, calls this nothingness energy. And that's not very novel, okay? First of all, Richard Feynman tells us that, that they have no idea what energy is. He says in one of his lectures, he says, it is important to realize that in physics today, we have no knowledge of what energy is. Okay, so we don't know what energy is, and that's the energy that gave rise, that's the nothingness that gave rise to something. Great. And we don't know what energy is. So that's a poor start right there. So how does Krauss get something out of nothing? Well, he says you take positive energy and you add it up with negative energy. We're talking math here, right? And you combine it to form nothing. Okay, essentially nothing. You can also break it apart into positive and negative energy. which somehow morphs into positive and negative virtual particles. Particles that pop in from the void, and they're going to look at those particles. Don't look at the word particle, because that's not what they're talking about. They're saying, look, this bundle of energy just popped in from the void because we need it in our equations. And then suddenly it goes back into nothingness. It just lasts for a very small amount of time to allow the mathematician to get his equations right. Then it goes back, like one of these traditional spirits, goes back and forms the fabric of space. That's what you're supposed to think about these. These particles. They're not really particles. What they are is just ad hoc variables that they need in their equations. And they stand for energy, which is a concept measured in kiloelectron volts or in ergs or in whatever they measure, depending on the type of energy. So they're talking about quantities. They're not talking about particles. They use the word particle, which is very misleading. And to top it off, they just put the word virtual, saying, it just comes in when the mathematician needs it, period. So that's it. You reach your own conclusions. And Stephen Hawking already explained all this, before Krauss did, which is, to me, makes it worthless to buy his book, or for you to go, to recommend it for you to go and see it, because to buy it and read it, because it's the same old, same old. You read one of these books, you read them all. Believe me, I've read several of these books, and they all say the same exact thing. There's nothing different between any of them. They all say the same thing in different words. So you don't need to buy any of these books anymore, because they all say the same thing. And you might say, well, this guy says it better than that guy. Yeah, maybe. I don't know. They all say the same thing. And Hawking says it in his book. He says, you can see how he creates something from nothing again here. Quantum theory tells us that particles do not come from within the black hole. He was talking about black hole. That was the context. But he says, but from the empty space just outside the black hole's event horizon. He puts empty in quotations. And so it's not quite empty. And he clarifies. He says, we can understand this in the following way. What we think of as empty space cannot be completely empty. So we don't have nothing, okay? We have something. What are those something? Pairs of particles of light or gravity that appear together at some time, move apart, and then come together again and annihilate each other. Unlike real particles, they cannot be observed directly. No kidding. I thought physics was based on proof. Here, or experiment or verification. Here they say you cannot observe it directly with a particle detector. One of the partners in the particle-antiparticle pair will have a positive energy, and the other one will have negative energy. So what did you learn today? Well, not much, son, not much. You don't learn much with these people because they keep going around, with semantics. It's just a circle. They start out with saying, oh, I can show you how we create something from nothing, start with nothing, then I create something. What do you mean you start with nothing? What's the process? What's the mechanism? What's the cause? What triggered this thing to happen? And they start out by saying, well, see, we start out with energy. What is energy? Is that nothing? Well, you see, it's positive energy and negative energy. You add them together and you end up with nothing. Oh, I see. And then you take nothing and reverse the process, and you can turn it into two particles. What do you mean two particles? Yeah, see, because you have a negative virtual particle and a positive virtual particle. I thought you were talking about energy. Well, yeah, they have energy. And so suddenly this energy turns into particles. And from particles, yeah, of course, then it's a piece of cake. Then after that, you can create the entire universe, because now these particles, they expand, they throw photons at each other, or who knows what, So now they can create this ballooning of matter. The tricky part is that tiny bit where they go from this concept called energy, which is a quantity, and they suddenly turn it into a particle. They give you the impression they turned it into some kind of ball. So it's like you take love and you turn it into a heart. Oh my God, that's scary, I mean, as long as love remains love, we're okay. But when love turns into a heart, I don't know. It gets a little trickier at that point, because that's how they come up with something out of nothing. That's the process. Okay, so was it Stephen Hawking who came up with all this? Was he the first guy? No, he did come up with that. He talks about it in his book, but here you have some other authors that already beat him to it. First, you have this fellow Alexander Vilenkin, and he came out in 1982 paper, "The Creation of Our Universe from Nothing," and that was almost what, almost 30 years ago, 30 plus years ago. So Mr. Lawrence Krauss did not invent this stuff. You should probably go to the original sources where he got his information. Someone already talked about it. Turns out that this guy wasn't the first guy either. He had someone before him, Edward Tryon. In 1973, in the British scientific magazine Nature, Tryon came out with a scientific argument. Scientific, I love that one. Argument that our universe might be the result of a quantum fluctuation of the vacuum. In his two-page paper titled, "Is the Universe a Vacuum Fluctuation?" Tryon would propose the very strange idea that our very large and very old universe could have come from a quantum fluctuation of empty space, the vacuum. And obviously they talk about empty, and they put that word empty. First of all, that's a terrible qualifier for space, because space is a synonym of empty. So you have an empty, empty, and it turns out that empty, empty is not, it's not empty at all. It's like Humpty Dumpty. It breaks and it is made into pieces. Okay, so empty space is not empty at all. And so in fact, he would describe this vacuum as nothing. And sometimes not quite nothing, which I like better. Yeah, more than likely he described as not being not quite nothing. And I think this would make him our first nothingist. Okay, fine. Prime would use Tolman's idea that our universe could have zero energy. Okay, and he learned this from a fellow named Peter Bergman. Okay, fine, to help him explain how our universe could have come from nothing and not be violating the law of conservation of energy, which is something that concerns them, right? He would also describe how our universe has virtual particles that pop in and out of existence at the quantum level of empty space. They keep talking about empty space, and they talk about particles coming out of empty space. How do they come out? Well, because you take a positive particle with a negative particle and you end up with nothing. That's how they do it. That's their nothingness turned into somethingness. Okay, so where did this guy get all this stuff from? Well, he got it from another guy in 1934 who wrote a book called Relativity, Thermodynamics, and Cosmology, with the idea that if you take all the mass positive energy and all the gravitational negative energy and add them up, they will cancel each other out, leaving a universe totaling zero energy. Okay? So you see how they're doing. So, first of all, I just want to point out that Lawrence Krauss did not invent any of this. Neither did Stephen Hawking, who wrote about it in his 1988 book, A Brief History of Time. You take it all the way to this Tolman guy. He's already talked about it in 1934 about energy, positive energy plus negative energy. You add them together, you end up with zero energy, and that's the original state of the universe. And suddenly from this zero energy, you divide it in positive and negative, you end up with not energy, you end up with particles. So you end up with a round ball that came out of this smoke, this energy, which we don't know what it is, obviously. That's the story of energy, of nothing, of something from nothing. Okay, so you might wonder if, even if this Tolman guy was the first guy to come up with this notion. But see, one of the questions that pops up constantly is, why is there something rather than nothing? Why don't we have a universe with absolutely nothing? And, many times they answer that by saying, well, then you wouldn't be around to ask that question. So they turn that around into this anthropic type principle notion where you would be asking the question if it weren't so. That's the answer to that question. But see, this question already it was. Here's the question, by the way. Just put it up there for reference. Okay, why is there something rather than nothing? Okay. And you know, where do you get these questions? Did these guys come up with it for the first time? And when you take it back in time, you find out that, you know, people have been asking these questions for quite a while. Here we have Mr. William James. He was a philosopher of the 19th century primarily. He says, how comes the world to be here at all instead of the non-entity which might be imagined in its place? So people were already wondering about these things long before, you know, any of these other quantum guys came up with it. Okay, so it's not the first time we humans hear about it. Okay, these people have been borrowing some of these concepts from 19th century folk who already ponder these questions. Why is there something instead of nothing? Okay, and how did we get here? And how did matter come into being? They've already asked these questions. And a lot of that had to do with religion. You know, people were wondering, you know, if God created everything, and the scientists say, well, if God didn't, then what did? So that was how the question came up. And all I'm saying is this question's been around for quite a while. Okay, here's another fella who talks about this because it kind of falls in line with what the relativists and quantum mechanics, you know, these mathematical physics, what they've been saying for a while, is that, you know, all the nothings are always somethings. And this notion has also been around at least since the 19th century. Here is Mr. Victor Hugo, and he was a French writer. He wrote Les Miserables in 1862, and in it he says, there is no such thing as nothingness, and zero does not exist. Everything is something. Nothing is nothing. Okay, I think that pretty much summarizes the mathematical physics. That's mathematical physics in a nutshell. He's saying there is no such thing as nothing. Was he the first guy to say this? No, you take it a little farther back and you end up with Mr. Aristotle. And Aristotle already asked this question. He analyzed it in a lot more detail than a lot of these guys. You know, you should simply go to the source, to Aristotle. He says it here. He says it in his book of physics, fourth book of physics. He says, he talks a lot here. I just took a couple lines from his book. It's quite extensive. He analyzes in quite a bit of detail. He puts his argument quite well, whether you agree with it or not. But he really goes in fine detail of why he believes there is no such thing as a void or nothing. And he says the question, what is place? And I guess he was referring to nothingness there because he was trying to figure out what do we call the location an object occupies once we remove the object. Is there such a thing as a place that the object occupied? Okay, and he said presents many difficulties. Moreover, we have inherited nothing from previous thinkers. He is throwing dirt on his colleagues, okay, whether in the way of a statement of difficulties or of a solution. Place is thought to be a kind of surface. And as it were, a vessel, a container of the thing. And this is interesting that he used the word container because, yeah, a lot of people talk about the ether, for example. And they can't make up their mind if space is equal to ether, space is ether, or space contains the ether. Supposedly a bunch of particles in there, you know, something like that. I don't know what they imagine when they say ether, but sometimes they equate it with space. Sometimes they consider space as a container, and in that case, you would have to specify then what is space if the ether is contained within this barrel. Okay, now you got to identify the barrel. But the most important argument that I saw in Aristotle's, and he's got several arguments, by the way. Okay, this I'm just pulling one out, which I thought was the most salient one, and that's, but not even movement in respect of place involves a void, for bodies may simultaneously make room for another one, for one another. What is he saying? He's saying, look, if you take an object and remove it, something immediately occupies that same space. Could be air, could be water, could be some seen or unseen, could be the ether for all we know. So what he's saying, what Aristotle is saying, is there's no such thing as a void because as soon as you remove something from its location of its place, something else occupies it. It's like a vacuum, creates a vacuum, and a vacuum, I think, I can't remember the exact statement. It's something, space abhors a vacuum or something like that. I can't remember now the exact phrase, but essentially Aristotle was saying that. He says, nature, that's what it was. Nature abhors a vacuum. There's no such thing according to Aristotle, right? You remove something, something fills that same space. So there's no such thing as nothingness. And all these people essentially concluded in the same way. We've been talking about what Aristotle, we talk about Victor Hugo. All these people are saying the same thing, all the way to Mr. Lawrence Krauss. They're all saying, there's no such thing as a vacuum. There's no such thing as total emptiness or empty space, as they like to say. It's a redundant term. It's oxymoron, empty space. I mean, if space is empty or a synonym of emptiness, what are you saying? Emptiness? What does that mean? But they had to say that because they don't believe, they never figured out that space is completely empty. They never concluded that. In fact, they need it for one of the things that I talked about in the numbers lecture. You're going to count. If you're going to count, you're going to have to count something. You can't count nothings. What are you going to count? 5 nothings, 1 nothing, 2, like the count in Sesame Street. 1 nothing, 2 nothing, so on. No, you only can count some things. You count apples, you count oranges, whatever you count, but it's got to be something. And so since mathematics only deals with counting and measuring, you can only count and measure some things. Space disappeared from their lexicon, from their language, from their jargon. They don't have a word for space, in other words, for nothingness. And so they had to turn space into something as well, because they had to give it some physical properties, okay? And that's the big problem. That's where the problem starts. Okay, in order to get a real handle on space and, why it's considered to be something, you have to go all the way back in time and look at the history of this thing, how this thing evolved over time. And I'm going to go over that starting on Wednesday. So stay tuned if you're interested in the subject. It's going to get more interesting, that's for sure. You're going to see a little bit of history and how the notion of nothingness changed over time. And okay, but we'll see you on Wednesday then. See you then. Bye-bye.